Yes, assalamu alaikum. Today we will have a look at memory management. In particular, we're going to have just a simple review to information related to memory, okay, that you have studied in computer organization and architecture in a simpler way, okay? So after we look at this, which is basically a review of memory structure, then we look at how memory is allocated to a process, okay, and how is it managed as well. And when we talk about that, we need to differentiate between logical and physical addresses, okay? Talking about this will get us into managing memory, looking up physical addresses, how the memory is allocated to a process, and that will lead us to something you have studied before, I think, which is paging, right? And the TLP, okay? Page hits, page faults, and so on. This is the exact tables or detailed topics that we're going to discuss in relation to memory management. So we start by a review. Basically, memory, when you look at it, it comes in two main categories: volatile and non-volatile memory, right? So here we're talking about volatile memory. So the volatile memory, we have two main types of it, basically the static RAM, random access memory, and the dynamic RAM, correct? And there are lots of differences between these two in the way they were manufactured, and how expensive they are, and where they are used, okay, or how the data is stored in there, if we're going to talk about the physics of them. So this is a table that gives us a simple like comparison between the two. It's actually a summary of what you're going to see on the next slides. Okay? So SRAM, it is much faster than the DRAM. The static RAM is much faster than the dynamic RAM. And it is very expensive. Basically, that's due, one of the reasons is that it is made of 6 transistor circuit. It is made of 6 transistor circuit, right? And it is used only for highest top or the topest caching or the topest level of memory. So the computer system has only very few of SRAM, right? And basically the information that's saved in there stays there as long as there is a power, okay? There is a power passed to it. This is why we call it what? Volatile, right? The dynamic RAM is used for main memory, okay? So SRAM is used for cache level 1, 2, 3, okay? And the DRAM is used for the main memory. It's also used for the frame buffer on a graphics system, the frame buffer, okay? That's a DRAM. In fact, it's also used with cameras and so, because the DRAM is very sensitive to light. Sensitive to light. It is made up of one capacitor and one transistor circuit. One capacitor and one transistor circuit. And in terms of the size, it's too small, okay? It is actually 13 multiplied by 10 to the power minus 15 farads, okay? It's small. And it has a leakage. Leakage means after a certain amount of time, it will lose its current, right? And by that, definitely the data will be lost. It's like within 10 to 100 milliseconds, if the current is not passed through, then it will lose the information in it. But there is no problem with that, because we know the CPU cycles, or for executing instructions, they need only maximum few CPU cycles, right? And some instructions, they only need one cycle, right? And these cycles, they do happen in very fast or very short amount of time. So in fact, the refreshment is done for the DRAM almost every 64 nanoseconds, okay? Which is much less than what it needs, okay? That's great. So refreshment means, okay, periodically, every bit is read and written back to the DRAM. That's what happens in reality, okay? Every short amount of time, because they are volatile, right? And there are techniques that could be applied with DRAM to correct a particular bit if it had been corrupted, okay? So basically, these are called error coding or error correction coding mechanisms, discovering what? A bit that had been corrupted and being able to correct it, but one single bit, if you have studied about that in organization. So what is it, the DRAM? The conventional, okay, view of DRAM is what? Number of cells, okay, the cells are partitioned into D supercells. So we have a number of D supercells in here, in this plane, okay? Each supercell has what? W DRAM cells. W DRAM cells. And a DRAM cell can have one bit, right? One bit. So W, how many DRAMs in one supercell? That will make, most likely, the word, right? The number of bits that can be saved in a supercell. Okay, so I have a number of supercells. Each consists of number of cells, okay? And then these supercells, they are organized in a rectangular form, Now, to access a particular supercell, then we need a row and a column, right? To retrieve, you need a row and a column. Now, so the row and the column determines the address, the actual physical address of a supercell. We need a row and a column. Now, the row and the column is supplied using appropriate pins that are connected, okay, to this structure. Later on, we'll see that we have much more complicated structure. So sending the row, okay, then sending the column, we identify a particular supercell. That supercell, okay, can be later on written to what? To the bus, right? It can be written back, where the CPU can get this kind of information. But what happens whenever a row is sent to this structure, the whole row is copied to the internal buffer, row buffer, and then waiting for the column to be sent, then that particular cell, okay, so first, once we receive a row, it's called the RAS, right, request. When it's received, the whole row is copied to the internal row buffer. And then after that, waiting for receiving what? A column identifying a particular supercell, and then it's copied back. So this is the actual exchange with memory. That's how it happens in a very small, simple scale, to understand how it really happens. But memory is not only few super blocks, right? It is much more than that. It's in terms of gigabytes nowadays, right? So there should be something else. Now, why we have this arrangement in the first place being rectangular format? Can anyone tell me? Why we have a rectangular format arrangement of supercells, not an array? I mean, just basically linear arrangement. This is hardware connected with pins, right? Right? For example, in here I have how many rows? 4. Columns? 4. How many elements? 16, right? So if I am to use the pins here, how many pins I need with this structure to send a row address? How many? How many I need? 4. No, I'm talking about the row. Okay, the row. How many you need? One, two, 4, 5, 6. What's wrong? What's wrong? Okay. How many digits you need to represent? Well, if you have 8 digits, then what's the maximum number you can represent? 2 to the power 8, right? And if you start from 0 in there, so that's the 255, isn't it? Okay, so having this kind of combination in there, okay, imagine that you have them linearly, okay, 16. How many pins you need? 2 to the power what equals 16? Yeah? But if you have only 4, 2. Okay? So you need less pins, right? Less pins, much less than what you really need, and especially if you're talking about what larger sizes of this kind of cell, right? So that's the idea, okay? But the disadvantage is what? That I have to send it twice, right? One time I send the row, and then the other time I send what? The column. Anyway, that's not our concern. So basically, the actual DRAM is an arrangement of multiples of this. Multiples of this structure, okay? Now we call them a module, okay? So DRAM chips are packaged in memory modules that are plugged into the extension slot on the main memory board or the motherboard. So we have a number of them, okay? So we have module DRAM 0 up to 7, for example. So we have 8 of them in this case, okay? And we would be having a particular, what? Pin arrangement, okay, to connect these modules. So we can have the DIMM, for example, and in that case, we can read what? 64 bits at a time, right? So depending on the arrangement of pins that you are using. So number of modules. And then we have an internal, what? Buffer. Now, this is connected directly to what we call the memory controller. Memory controller. So the memory controller is the one that sends what? The row and column, right? But if I have modules now, and we want to retrieve particular information from one module, then we send what? The module number as well, right? So we send K, I, and J. So the memory controller sends what? K, I, and J, where K is the module number, okay? So that's enough to retrieve any information that you want from a DRAM, okay? So basically, this is what done by what we call the memory controller. And the memory controller is what? Hardware, right? Okay. Where is it? This circuitry memory controller, where is it on your computer system? CPU? شو رايكم? What do you think? This chipset, okay, is within what? Is it within the CPU chip? Is it? Where? Yeah, but in actual manufacturing, okay, this also is within that chip, okay? And basically, just the wiring to the memory bus will be to only send the addresses, okay? It's within that. Anyway, that's the arrangement of it. But however, okay, as what we're going to see in a while, which is the memory management unit, it can be within the, actually the CPU, and it could be also as a separate chip. Now, the types of DRAM, we have different types of DRAM. This is a review only, and I'm not going to make it like a computer organization architecture, okay? But however, I need you to understand that there is a memory controller. Memory has a particular structure. To retrieve from there, in fact, what happens, okay, that when a physical address is passed to the memory controller, okay, the memory controller put it in the appropriate format, okay, on these pins to retrieve the data, okay? To retrieve the data. So we have number of the RAMs, okay? These are the enhancements with DRAM. Currently, for example, what is used in Core i7 is DDR3 as DRAM, if you notice, right? You are using Core i7, most of us, isn't it? Okay, but however, there is also DDR4, okay? Now already in the market. The Rambus DRAM is the most powerful, and the VRAMs or the video RAMs, they are actually using the very first version of DRAM. ROM, on the other hand, it is what? Volatile or non-volatile? Non-volatile. So basically, it keeps what is stored in there, right? It's, well, read-only memory, but however we write it, right? And we could write it once only, program it one time, or we could program it multiple times, which is the erasable program, ROM, okay? But the EEPROM, to program it, we need a special hardware to do that kind of programming, to write to it. However, the EEPROM, which is the electrical EEPROM, and if you've been doing that, okay, writing on it and erasing many times, okay, basically you just have a circuitry where the chip is in there, okay, and you have the appropriate wiring with your computer, you can always, okay, rewrite it, erase it, and rewrite it. So that is called what? The electrical erasable PROM, right? Programmable ROM. But however, there's always a number of times that you could do that, okay? But we don't notice it because we don't reach up to that, okay? So for example, this one can be erased 10 to the power 5 times. However, this can be only 1,000 times, okay, or in rounds of 1,000 times. Flash memories, they are actually based on what? The EEPROM, right? And what we have as SSD, the solid state disks, also, they have some similar technology. And most of these actually ROMs, when we, I mean, the kind of information saved on them, they are programs, okay, small programs, and we call them what? Firmware. Except, of course, for the case of the flash memory or the SSD, where we can save actual data. Now, the most interesting out of all, okay, to look at the evolution of the manufacturing and usage of these memory storage devices, I mean, including the SRAM, DRAM, okay? So we have SRAM here, we have DRAM, and we have even the rotating disks, okay, the external, or the, we call them the storage devices or secondary storage devices, like disks. And the CPU itself, okay? The most interesting thing, so this data is captured from 1980s to 2010. 1980 to 2010. The most interesting column here is the last column. So here, we are recording, for example, the cost of the SRAM for every megabyte. In 1980s, it was 19,200. That's very expensive, right? And in 2010, it is only 60 for 1 mega of SRAM, okay? It's much cheaper. How much cheaper? 320 times cheaper. Okay? 320 times cheaper than it was in 1980s. So this is what we see, okay, the comparison of 2010 to that of 1980s. 320 20 times cheaper than it was. And in terms of access time, the access time for it was only 300 nanoseconds, while in 2010 it is 1.5 nanosecond. And that gave us the 200 times faster. Okay, 200 times faster. While if we look at the DRAM, okay, the price was 8,000. This is for 1 megabyte. Currently, it is what? 0.06. And that's an improvement of 130,000 times cheaper. It is much more cheaper, right, becoming the DRAM than what SRAM is. And if you look at the access time, it was 375 nanoseconds, and in 2010 we had 40 nanoseconds. That's only an improvement of 9 times. Only 9 times improvement. If we look at the size, the improvement is 125,000 times smaller than what it used to be. That's a lot, right? Okay, we can explain this. This is good, right? What about this? Access time. Only 9 times better. Why? Not really. The improvement in science, could have it much more faster. But we choose what? We choose to have much more DRAM in the same space. So the density is much higher, right? We have more dense, what? DRAM. And for that, the access time, okay, improvement is not really that much. But however, we gained much more. You could have much more DRAM than what we used to have in a very small area. So density, okay? The manufacturers, they choose density on what? On access time, where access time is still acceptable, okay, for that. And that's why now we can have gigabytes of DRAM easily added to our computer systems. While last time you are limited. There are few slots there for you to add, and basically if you could have 128, that's great, okay, the maximum, okay, for expansion slots that you have on the motherboard. But now you could have a piece, okay. The time they had the 1 gigabyte piece, okay, it was really something revolutionary in DRAM, okay, to have it as one piece, okay, imagine. So that's why we see this number. So this is what's interesting actually about this. If you look at the rotating disk in terms of, look how cheaper it is now, okay? It's 1.6 million times cheaper than what it was, okay? And in terms of the size, it is again 1.5 million times smaller, because I consider the capacity as well, right? So, but in terms of seek time, it's only 29 times shorter, the seek time, than what it used to be. Why? Again, because density, isn't it? So we could have, okay, larger hard disks, right? And if you look at the CPU in terms of the clock rate, now we have it 2,500 times, okay? And for the cycle time as well, the same. For the cores, the improvement was too slow, okay? Currently, we have what? 4. But once you reach 4, then there is no limit, right? It goes 8, 16, and so, okay? But, of course, there will be problems with cooling and all that kind of stuff in terms for manufacturing. And the need for it as well, the need for it. Okay, as for the effective cycle time, we have an improvement as well, 10,000 times, okay? So I hope that this gives you, okay, the kind of improvement that we have and the differences between SRAM, DRAM, and why this one is improving slower than the other one, and so on. So in a computer system, in fact, we are using different type of storage, okay? From the registers, okay, who have what, zero latency in terms of accessing them, and the levels of caching, okay, that we have in the system, such as L1 cache, L2, L3 cache. These basically within the CPU environment, and we use the SRAM for them. And in most of the time, when you have multi-cores, the L3 cache is shareable among the different cores, while each core has its own L1 and L2 caches, right? Always the L1 cache would be faster and smaller and more expensive than L2 cache, and so on if you go with the comparison, okay? And the DRAM, you see that it implements what we call the main memory, okay? Always in this hierarchy, so of course we have after that the secondary storage, as well as the remote, the storage of remote data that are on servers, and we store it locally. That happens frequently when we access like web servers. We cache some information from these web servers. So caching. Caching, what is it? Caching basically is this concept, okay? You have a slower, larger, and cheaper type of storage, okay? And we store a portion of the data that it has in a more expensive, faster, okay, and smaller kind of storage, okay, in general, right? So this is the concept of caching, a portion of. This is exactly what we're doing when we do the caching, for example, here on a simplest concept, okay, when we access, okay, web servers. Web servers, you are accessing certain HTML pages in there or contents. You're not continuously accessing that data from the server. In fact, these are cached, right? And they have certain lifetime. As long as they are not updated, there is a policy with HTTP protocol for that. So you cache them, and when you want to see them again, they're already there, cached on your hard disk, okay? So your hard disk is much more faster and smaller than the remote hard disk, which is basically that exists on a big storage system on these like sites who are offering this kind of services. Okay, so this is the simplest what caching. However, we have other type of caching. For example, in there, the highest level of it, okay, when we talk about CPU registers, okay, that can be used to cache. But cache what? Cache basically 4 bytes or 8 bytes words, okay? And the latency is 0. And who's responsible for this kind of caching or managing it? The compiler, right? The compiler, your code, basically, when this data is saved in that register and then moved to that register and so on. So the compiler that manages that kind of caching. That's the highest and the fastest caching that we have in a system. However, on the other hand, also we have caching that is implemented by hardware. And that is the caching when we have what? When we have a logical address, okay, an address that's generated by the CPU, and we would like to know what is the physical address corresponding to this logical address of a process, okay? That kind of relation. To know that physical address, basically, we can, trigger the TLB, which you have studied, right? Trigger the TLB to know what is that address. And then later on, knowing that address then can be sent to the memory controller to put it in the format that we have just seen. So this step, okay, which is the MMU step, MMU hardware, mainly TLB hardware, okay, comes before, okay, before the CPU communicates with what? With the memory controller to send the actual physical address, okay? So this is controlled by that. And we also have L1, L2, and L3 caches, and these basically, they are to cache 64 bytes. 64 bytes. So here we cached before, we cached addresses. Now could cache data. And these are implemented all in hardware, SRAM hardware, right? We also have caching of virtual memory, and that is implemented by combination of both hardware and operating system, which we're going to talk about as well. And then the rest of them where we cache portions of the data that is saved on the disk, we cache it where in memory. For example, when you read from a file, your file is a huge file, got lots of data in it, and you are interested in only reading one portion of it, say an integer somewhere there. But when you issue that read, in fact, not only that integer is read, what is read is much more than that. One whole block is read. One whole block. And it is cached. Cached where? In memory. Okay? So it was on hard disk and then cached in memory, one whole block. What you will use out of it, okay, is what you requested, is only that integer. However, the whole block is cached. So in the future, if you request additional information, and it happens that that additional information requested is within that block, then no need to access what the hard disk can. We can access what? The block that had been cached in memory. So making things much faster, because talking about what? Mechanical devices and memory. The access is much more faster. And other ways of caching, such as if you cache, for example, a file that is on a network storage using the a network file system, okay, you cache that file locally as well on your local storage. That kind of access is much more faster. And later on you might see that even you can cache portions of your file on secondary, that used to be on secondary storage device. You can choose which portion of the file to be cached in memory, okay, so that you can access it directly from memory, as well as you can cache the whole file if you have enough memory for that. So that's the principle of what? Caching. So we're getting portion of information cached in or saved in where? Higher level, that is faster, smaller, more expensive. Okay? Why? To make things much more faster. Okay? With that comes lots of techniques and problems of doing so. So that's just a review. Okay? And I hope that it will help us in understanding